Hey gang, welcome back. We're starting lecture number 28, and this will be Magnetism Part 2. And in this lecture, I want to discuss the electromagnetic spectrum, something we're going to come back to in a later lecture. Okay, so electromagnetic spectrum, let there be light, because I know you're all in the dark right now. All right, so in the last lecture, we discussed this. Recall wiggling electric fields, WEF I called it, produce wiggling magnetic fields, WMF, and wiggling magnetic fields, WMF, produce wiggling electric fields. Okay, and together they produce electromagnetic radiation, EM radiation. Okay, and this is what I want to talk a bit about today. Good. So here's yet another law of nature, the way we find the world, our universe happens to be. Uh, all electromagnetic radiation travels at the speed of light, and the speed of light is a constant. And we'll talk about this, okay? The speed of light is what is the speed of light? Well, we use the symbol C. Can you guess why? We use the symbol C for the speed of light because it's a constant. Amazing, right? And in terms of meters per second, it's 3 times 10 to the 8th meters per second, which is hard to get a grasp on. But it's also, if we convert, it's approximately 186,000 miles per second. That means if you take a flashlight and you shine it in the sky in 6 seconds, some of that light will be over 1,000,000 miles away, right? 5 seconds, 6 seconds will be 1,000,000 miles away. The distance to our sun from Earth is approximately 93 million miles. If light travels at this speed, how long does it take to get to the Earth? Well, you could calculate if you know the distance and you know the speed. It turns out it takes approximately 8 to 9 minutes for light to get from the surface of the sun to the Earth. That means if the sun went out at this instant, we wouldn't know about it for another 8 minutes. So when we look at the sun, we're looking back in time approximately 8 minutes. When we look at certain stars in the sky, depending on their distance, we could be looking back a year, 2 years, 1,000 years, 1,000,000 years, billions of years. So every time you look up in the sky, you're looking back in history. Some of the stars we see with the Hubble telescope or some of the galaxies may not even exist today because it took billions of years to get to us, and today, at this instant, they don't exist, so we wouldn't know about it for another few billion years. All right, so the speed of light is a constant. We're going to use this fact in a little bit when we discuss the electromagnetic spectrum. Okay, so the speed of light is the fastest speed allowable by nature. We've never seen anything violate this law. Okay, electromagnetic radiation may be described as a wave. Again, we'll have more to say about this later. And there's two characteristics I want to talk about of waves. One is their wavelength, and the other is their frequency. Okay, if I make a wave, I'm just going to, any kind of wave, water wave, any kind of wave, okay, wiggling, the distance, the shortest distance between any two repeated points, or here and here, that's the shortest distance. The shortest distance between any repeated points is called the wavelength. Okay, so the wavelength can be measured in meters, nanometers, micrometers, kilometers, can be measured in anything. So the wiggling, the distance between wiggles is called the wavelength, the minimum distance between a repeated part. The second characteristic is the frequency. Frequency is essentially how many wiggles per second, how fast the oscillation is. Number of wiggles or oscillations per second, this unit's called a hertz. Okay, after Heinrich Hertz, discoverer of early radiation. All right, so we have two things, frequency and wavelength. Wavelength, we use the symbol lambda. That's the Greek symbol lambda. Now, the frequency and the wavelength are related to the speed of a wave. Speed of any wave, watch this, any wave is this. V equals the frequency times the wavelength. Any wave. Great. For electromagnetic radiation, the same law holds, except now the speed of electromagnetic radiation is C equals F lambda. Now I'm going to talk about these for a second. The speed of any wave. This could be a water wave, a sound wave, and so forth. Okay? Again, we're going to have a whole chapter on waves, and we'll talk about this later. So a water wave could have any speed, but the speed for electromagnetic radiation is always the speed of light. Now I want you to look at this mathematically. Okay? This is good review. If C is a constant, frequency times wavelength always must equal this number, 3 times 10 to the 8th, or 186,000 miles per second. That's a constant. So what type of mathematical relationship is this? Frequency times wavelength is a constant. It's only a constant for EM radiation, not for any other wave. If frequency times wavelength is a constant, this is what? Frequency and wavelength are inversely related. Do you remember what that means? If I made the frequency 5 times greater, the wavelength would decrease by 5 times. If I decrease the frequency by 30 times, the wavelength must increase by 30 times. This is an inverse relation. Do you remember what other inverse relation we discussed? Do you remember? That was Boyle's law. Remember? Remember Boyle's law? Constant temperature. Pressure times volume is a constant. So if you double the pressure, the volume decreases by 2. Same type of relation. This relation, that the frequency times the wavelength is equal to a constant, is going to lead us to what's called the electromagnetic spectrum. So let me kind of erase and get a start on some of this. So what I'm going to do is I'm going to take an electric charge, I don't care, positive, negative, and I'm going to wiggle it. Okay, oscillate it, all right, whatever you want. Let's get fancy, oscillate. I'm going to take an electric charge and I'm going to oscillate it. Now remember, frequency and wavelength are inversely proportional. So I'm going to draw this table. Oh, I'll make it nice and big. And here I'm going to say large lambda, that means small frequency. Okay, here I'm going to increase the frequency, So here I have large frequency and small wavelength. Remember, they're inversely related. Before I wrote over here, I wrote that the energy of a wave is directly proportional to the frequency. But again, if we just stop for a second and think of common sense, imagine I have a jump rope, okay? And I wiggle it. That's my frequency. If I wiggle it, you agree, I'm putting energy into the wave. Now, suppose I wiggle it really fast. The faster I wiggle it, the more energy I put in. So energy is directly proportional to the frequency. The energy of the wave is directly proportional to the frequency. So if this is a very small frequency, that means the things on this end have very small energy. As we increase the frequency, we increase the energy, as you'll see. So if I take an electric charge and I wiggle it, remember, if I wiggle electric charge, I produce wiggling electric fields and wiggling magnetic fields. So I'm producing wiggling electromagnetic fields. If I wiggle it the slowest I can wiggle it, these are called radio waves. Radio waves. Okay? If I wiggle it, so radio station W Kiss My Butt, whatever you want to call it, broadcasts, they're putting wiggling electric fields out and wiggling magnetic fields out. Okay? And that's our wiggling electromagnetic radiation. Okay? So they're taking electric charges and they're wiggling it at a certain frequency, whatever the frequency, AM or FM. I'll talk about kilohertz and megahertz later on when we talk about waves. If you take electric charge and you wiggle it a little faster, okay, you get something called a microwave. wave. And I'll review all of this. Okay? If you wiggle a little faster, you get a microwave. If you wiggle a little faster, you get something called infrared radiation. Okay? Another name for that is heat. Okay? Then I'm going to put a gap here. Okay? Kind of like Michael Strahan's teeth, a gap in the. We'll come back to this gap. If I wiggle the electric charge faster, I'm going to produce electromagnetic radiation that we call ultraviolet. Right? Light-skinned people love that stuff. They go to a machine, they pay people to have their cells killed because someone on Madison Avenue says, boy, you look so sexy with those dead cells. Okay? If we wiggle faster and go beyond ultraviolet, we get something called an X-ray. X-rays. So we're increasing the frequency, we're increasing the energy, and you can see that X-rays are certainly more dangerous than radio waves, unless you listen to certain radio stations. Right? Radio waves are actually passing through our bodies right now. And finally, if I wiggle it the fastest, we get gamma radiation. Okay, that's the most energetic. If you're exposed to too many gamma rays, what happens? You turn into the Hulk. No, you die, obviously. All right, all this together is called the electromagnetic spectrum. And once again, I'll come back to this in another lecture. Okay, this gap here between infrared and ultraviolet is our old friend Roy G. Biv. Does everybody know what Roy G. Biv is? It's the colors of the spectrum, right? Red, orange, yellow, green, blue, indigo, violet, in this order. So this right here, this gap is visible light. So if I ask the question, what color on the spectrum has the most energy? It would be violet. Which has the least energy? It would be red, has the longest wavelength, shortest. If I ask which wavelength, which radiation part of the visible spectrum has the shortest wavelength, it would be violet because they have the greatest frequency, inverse relation. Okay? So let's talk. What is a radio wave? What is visible light? What is visible light? What is everything on this spectrum? Everything on this spectrum is what? It's a wiggling electric field and a wiggling magnetic field. What is an X-ray? It's a wiggling electric field and a wiggling magnetic field. Suppose I took a flashlight, visible light, and I shot it towards you. And then I took an X-ray and shot it towards you. Which would get to you first? The X-ray or visible light? The answer is they get there at the same time. Why? Because all electromagnetic radiation moves at the speed of light. So gamma moves at the speed of light, X-rays, ultraviolet, radio, they all move at the speed of light. Which wiggles faster? X-rays certainly wiggle faster than visible light because they have more energy. So it wiggles faster, but they both travel, have the same speed. Okay? Trick question. Okay? So radio waves, wiggling electric and magnetic fields. Microwaves, your microwave. What is it? Wiggling electric and magnetic fields. Heat, wiggling electric and magnetic fields. Visible light, wiggling electric fields, wiggling magnetic fields. When you go to the doctor for an X-ray, wiggling electric fields, wiggling magnetic fields. And when you go to make yourself beautiful, no hope for me, but if you go to your tanning salon and make yourself beautiful, according to somebody, wiggling electric fields and wiggling magnetic fields. So this is the electromagnetic spectrum, wiggling electric fields and wiggling magnetic fields. Okay? In the next lecture, I'll come back and I will discuss more on magnetism.